Okay, so last week on Wednesday, we started the section 3.1 over the idea of functions. And what we talked about last time was this idea that you're probably used to thinking of when you think of functions from your other math classes or maybe even computer science. And we usually think of a function as some sort of rule that assigns, or maybe just assign as a rule. Maybe we'll just leave it there. We can worry about sets later. So what I mean is you can plug something into your function and then there's an output. So this is a linear function. If you plug in a value, a number x, you'll multiply by 3 and add 5. And here's some more complicated kinds of mathematical functions like the sine function in trigonometry. And here's the logarithmic function that you might have seen in an algebra class before now. And then to wrap up the day last time, we talked about this idea of a checksum, which is a particular kind of function that helps detect errors in credit card numbers when they're entered as a payment information on websites or usually websites, I guess, but also other places anytime you enter a card number. Okay. So this was kind of an elaborate method. It's just a little bit more complicated than just a straightforward mathematical function. So functions can have all sorts of forms, like this one. And what we're going to do today is pick up here on the next page where we look at the concrete definition of a function using set theory, the kinds of things that we learned back at the beginning of the semester. Okay, so for a function, we're going to start with two sets. Let x and y be sets. Then a function f from x to y is actually a subset of the Cartesian product s cross y. So in case you haven't thought of the Cartesian product in a while, let me remind you that this is just the set of ordered pairs. Where your first element comes from the set x and the second element in your pair comes from the set y. Okay, so a function is a subset of this Cartesian product. So it's a set of ordered pairs where for each element x in the set x, there's exactly one element y in the set y with x comma y in the function, x comma y in f. Okay, so this definition is very different from the kind of definition that you might be used to, where you think of a function as a rule, but it does relate back to the other idea, as we'll talk about going forward. So one thing before we do any examples is that we should talk about notation. A lot of the time there's the shorthand notation. So f is going to be the name of our function. And then we specify two sets, x and y. So what this would translate into, this symbolic form would translate into English as f is a function from x to y. And there's a few more things that we should point out here. Going back to our old idea of functional notation, this relates like this. So if you have some ordered pair in your function, so little x and y are in f, then we can write instead of this just f of x is equal to y. So what an ordered pair means is that the left element, the first element, is the input of the function, and y is the corresponding output. So this is how it would look in the old functional notation, which we'll actually be using most of the time anyway. And there's a few more things that I should point out. The set x is called the domain of the function. And the other set y is called the codomain. So you might already be familiar with those terms. And you probably also know about the range of a function. So let's go ahead and define that too. So the range of f, a function, is just the y elements that are possible outputs of the function. So in set builder notation, this would be the set of elements y such that x comma y is in the function f. So y is an output that corresponds to the element x being plugged into the function. Okay, so this is a little dense, I think, especially since we have this new weird ordered pair definition of functions, which doesn't really agree with our normal thinking. So let's go look at a simple example to make sure we can decipher what all of this really means. Okay, so here in my example is the first function that we're going to look at. My domain x is going to be the set with 1, 2, and 3 in it. And then y, my codomain, is going to be the set with a, b, and c. And here's my set of ordered pairs. There's 3 ordered pairs here. And what I want to do in this example is just determine if f, the set of ordered pairs, is actually a function. And the way we're going to answer this is using what's called an arrow diagram. Okay. And this is just an illustration of how f, the ordered pairs, pair elements of the 2 sets, x and y. So let's make our arrow diagram so that you can see how they work. What we're going to start by doing is to write the elements of the set X in a column like this. And I'll put an oval shape around them just to show that they're together in the set X. Excuse me. And then I'm going to make another column with the elements of the set Y. Like this, and let's go ahead and label that like so. And now what I'm going to do is draw an arrow for each ordered pair from the first element in X to the second element in Y. So for this first ordered pair, I'm going to find the element 1 in X and draw an arrow over to the element B. And then we'll repeat that for each of the other elements, each of the other ordered pairs. So here we have an arrow from 2 to C. And for the third ordered pair, we have an arrow from 3 to B. And then I'll label my arrows with the name of my function f. So what the arrows are doing here is they're pointing from the input value to the corresponding output. Are there any questions over the arrow diagram so far?
Why isn't there one that's pointing to A at the top?
A good question. That's because A doesn't pair up with any of the elements from X.
Oh, okay, that makes sense.
Yeah. Okay, so using the arrow diagram, how can we check if f is a function? And here's what we're going to do. So if f is a function, then there can only be one arrow from each element of X. So then there will be exactly one. One arrow from each element in the domain X. So looking at our arrow diagram, we can see that 1 has a single arrow, 2 has a single arrow, and 3 has a single arrow. That means that this particular set of ordered pairs actually is a function. Okay, any other questions before we move on? Okay, so if there aren't any questions, we'll move on to the next page and look at a couple more examples using these ordered pairs. And for these next two questions, we're going to try to answer the same question. Is f a function? Is this set of ordered pairs an actual function? So we'll want to make the arrow diagram and check to see that each element of x has exactly one arrow pointing to an element of y. So just start by making a column with the elements of x. Here we have 4 numbers, 1, 2, 3, 4. So it's a little bit different from the last one. And then y has the same letters as before, A, B, and C. And now we'll look at our ordered pairs, and we'll draw an arrow for each of them. So we'll get an arrow from 1 to A. From the first ordered pair, an arrow from 2 to B. For the second ordered pair, and then the third ordered pair will get an arrow from 3 over to C. So is this a function?
No, because 4 doesn't have something to pair with.
Good. So f is not a function in this case. And you're right, it's because 4 doesn't pair up with anything else. So in the arrow diagram, there's no arrow from 4. And if we look up at the ordered pairs in our set F, there's no ordered pair where 4 is the first element. So whether you're looking at the arrow diagram, this nice illustration, or you're looking at the ordered pairs, you can tell either way that this is not a function. Any questions over that? Okay, now we should look at this third example. We're going back to the first set X with just 3 numbers, 1, 2, and 3, and then Y is staying the same. And we have a new set of ordered pairs, F, and we want to figure out if it's a function or not. So we'll make our arrow diagram. There's the set X. We'll make another column for the set Y. Now we have 4 arrows to draw, 1 for each of the ordered pairs. So we'll start with an arrow from 1 to A, and then an arrow from 2 to B, an arrow from 3 to C, and then finally an arrow from 2 to A. So is this set of ordered pairs a function?
No.
I'm going to say no because
No.
2 goes to 2 different things.
Good. Yeah, that's exactly the reason. F is not a function. Because there are 2 arrows from the number 2. And if you look back at the ordered pairs, we can see that there's actually 2 different ordered pairs where 2 is the first element. So here 2 is paired up with B, and here 2 is paired up with A. Okay, good. So do you guys have any questions over this third example? Okay, so before we move on to anything else, just like to point out that these are the 2 ways that something could not be a function. So either one of your elements in your domain is not paired up with something in your codomain Y, or the other way is that you could have 2 arrows pointing from a single element. You could have a single element in the domain that's paired up with 2 different elements from your codomain. Okay, so that finishes up this first little section of notes. So maybe we'll take a minute here and we'll see if you guys have.
Professor O'Dell, can you scroll down, sir?
Just, yeah. There you go.
Thank you, sir.
You're welcome. Okay, so has anyone thought of any questions that you'd like to ask here? Okay, so since you guys don't have any questions, we should continue on. Since we have lots of extra time with the second part of my notes. So what we're going to start with here, or really continue with, are some common functions that you'll run across in discrete math, our current course, and probably in any programming course or programming project. These functions could very well come up. So the first thing I want to do is just relate back our set theory idea to the more common idea of thinking of functions defined using rules. And here's just a quick little example. Here's a function f from the real numbers to a set y, defined by this rule, f of x equals x squared. And then I also have to tell you what y is. It's, in this case, the set of non-negative real numbers. So the number is greater than or equal to 0. So this is probably a way that you're used to functions being defined. If you took a different math class like algebra or calculus or whatever, this is probably what you would see most of the time. So let's think about how this relates back to our ordered pairs. And it's like this. In this situation, the ordered pairs are, lost a word here. Ordered pairs are this set. So we keep the same function name, but now instead of thinking of the function as a rule or with functional notation, we think of it as a set of ordered pairs where the first element is the input and the second is the output. So we pair up x with x squared, and then we just have to specify where x comes from. And it's a real number, so we say x is an element of R, the real numbers. So the interesting thing about the ordered pair definition is that these actually correspond to the points on the graph of f. So even though this ordered pair definition feels new, it actually is related very closely to something that you're familiar with from probably all of your recent math classes. So they correspond to points on the graph. And maybe we can just make a quick sketch of this particular function, f of x equals x squared. We know this is the parabola, the basic parabola with vertex resting on the origin. Let's see, let's just plot a couple points and then connect the dots. Just try to make it symmetrical. And add a label there. Okay, so this idea of ordered pairs is, I just wanted to reiterate, actually very closely related to the idea of functions that you already know. Do you guys have any questions about graphs or the relationship between the ordered pair notation and the functional notation? Okay, so the next.
That's where I was still getting that up there.
Okay, yeah, that's fine. I can pull that back up. I'll give you a minute. Okay, so let's move on to this next function. This one is called the modulus operator, or modulo arithmetic. You might have heard the word, those words. And this is something that actually does come up quite a bit in programming. And here's what it is. If x is an integer and y is a positive integer, then we define x mod y, or x modulo y, to be the remainder when x is divided by y. So this is closely related to something that you learned in elementary school, just remainders when you're dividing whole numbers. We can do some examples. Like, what is 6 mod 3? And someone just shout out or type the answer in the chat. What would the remainder be when you divided 6 by 3? I guess, good. The answer is 0. Victoria wrote the answer in the chat. Because 3 goes into 6 2 times, and there isn't anything left over. Any questions over this? Okay, then let's just do a bunch more so that we can get comfortable with the idea. What would 6 modulo 4 be? Can you say that again? You got a little cut off.
2.
2, good. So 4 goes into 6 one time, and there's 2 left over. What about 6 modulo 5?
1.
Good. Yeah, so 5 also goes into 6 one time, and there's 1 left over. Let's try some more numbers. What's 5 modulo 1?
0.
0, good. Yeah, and in fact, any integer modulo 1 will always give you 0 because 1 divides everything evenly. It divides whole numbers evenly. What about 5 modulo 2?
1.
Oh yeah, 1.
1. I think someone said 3. Yeah, so if you put 2 into 5 one time, there's 3 left over, but you could put it in twice.
Yeah, that's true.
Yeah. Good. Let's do some more.
So basically what you're doing is you're taking like your first number and essentially you're dividing it by the second number and then you're getting the remainder.
That's exactly right. Yeah,
Okay.
so if we wanted to use division notation, we could just pick one of these, like 5 modulo 2. So what we're thinking about is we're dividing 5 by 2 using this elementary school notation. We know that it goes in twice. So we would multiply and then subtract. 1 is left over. So you might write R1 or something like this. So 2 goes into 5 twice with remainder 1, and the modulo operator is the remainder.
Okay, that makes sense. Like, I know that's a programming thing, but I was trying to like work it out in my head as we went along. I
Yeah.
wanted to make sure I was doing it right.
Yeah. So it's related to long division back in elementary school. What about 12 modulo 42? What would that be? Okay, so Victoria says 6. Does anyone disagree?
Yeah, wouldn't it be 0?
Okay, so we have 3 different answers.
Wouldn't it
6,
be 12
0,
though?
and 12. The answer is 12. Yeah, so 42 can't go into 12 because 42 is bigger than 12. So everything is left over.
That makes sense.
Yeah. Let's try this one. Just pick a large number. Modulo 2. What's the answer to this one?
1.
It's 1. Good. How can you tell it's 1, Nick?
Last digit's an odd number.
It's an odd number, right. So if I picked another big even number, what would the answer be?
0.
0. Good. So an important property of modulo 2, the operator modulo 2, is that if you plug in an odd number, you'll always get 1. And if you plug in an even number, you'll always get 0. So this is definitely something that I've seen show up in a programming problem where you need to figure out whether you're looking at an even number or an odd number. And using this modulo mod 2, we can detect whether it's odd or even because it'll give us a 1 or a 0. So a 1 for odd and a 0 for even. So this is maybe a handy little trick that you might use at some point in a programming problem. Okay, are there any questions over the modulus operator? Let's see. Is anyone still writing? No? Okay. So let's go ahead and go to the next page and see if we can answer this question. What day of the week will it be 365 days from today? Does anyone know the answer without looking at a calendar?
It'd be the same as today, just 1 year later.
But what day of the week? Like today's a Monday. What day of the week will it be?
Tuesday, right?
Yeah, Tuesday. That's the correct answer. So in 365 days, the day of the week will go forward by 1. So if today's a Monday, then in 365 days, it'll be a Tuesday. So let's see if we can work through why that's actually true. So let's just start at today and then count forward. Today is Monday. What day of the week will it be 7 days from now?
Professor, are you factoring in the leap year for this year?
No. So I'm specifically doing 365 days.
Yeah.
You're right, on a leap year, there's 366 days, so it would be a little bit different. Okay, so what if we just go 7 days in the future? 1 week. What day of the week will it be? Anyone?
Monday.
It'll be Monday, right? 7 days from now, it'll be another Monday. What if we go forward 14 days or 2 weeks?
Still Monday.
Still Monday. What about 21 days?
Same.
Same. Good. So if we go forward some multiple of 7, so a whole number of weeks into the future, then we're going to be on the same day as today. We're going to still be on a Monday. So let me write it this way. 7 times in days. That would be in weeks. So what we can do is subtract as many weeks as we can from 365, because we know when we go forward 7 days, nothing will change. The weekday won't change. So if we can subtract as many 7s as possible from 365, we can simplify the problem. And then we can use what's left over. That's otherwise known as the remainder. Do we have a convenient operator that gives us the remainder? Well, yeah, we just learned about it, right? So what we really want to figure out is 365 modulo 7. What is that?
I've been thinking about that. I think it's 1.
It's 1, that's right. So if you work it out using long division, or maybe, yeah, let's just go ahead and write it out.
I
It
wasn't
would
sure if it
be
was negative.
5. Wait, you're right. Sorry. The same one
Okay,
of
yeah,
them
let's
was
try the long
I meant
division and
wrong.
just double check. So 7 doesn't go into 3. How many times will it go into 35? Or excuse me, 36?
5.
5 times, and we get 35. So subtract, bring down the 1, and then the 5. How many times does 7 go into 15?
2.
2 times.
Whoa, 52 weeks. I see it.
Yeah, yeah, exactly. There's about 52 weeks in a year. So that's where that 52 comes from. And then here's the remainder. 1 left over. Good. So if you go 365 days in the future, you'll only advance 1 day of the week. So today's a Monday. In 365 days, it'll be a Tuesday. So just a little trick helps us answer this question using the modulus operator. Are there any more questions or any questions at all about this? Okay. So this next point, I think, will probably be our last topic for today. Oh, well, actually, there is something I want to discuss before we move on. So I told you that these things do show up in programming with some regularity. So what I did here was I opened up a what's called the Jupyter Notebook in the Python programming language. So we can, in these cells, just enter something in the Python language and have the computer run it. And in Python, the symbol, the %, is used for the modulus operator. So if we wanted to do, like our first example, 6 mod 3, we would write 6 and then the % 3. And then we know the answer should be 0. And of course, that's what the computer gives us. And we can just plug in a few more numbers that we saw earlier. Maybe 12 mod 42. So 12 %, 42. And then run that, we get 12. And then maybe we can try one of those really big numbers. Let's see, so 3, 9, 5, 4, 8, 6, 3. I think this is what we did earlier. And then just do modulo 2. And we get 1 since this is an odd number. If I change that last digit to a 2, we should get 0 since it would become even. Okay, so just a quick little demonstration of how you might use the modulus operator, at least in Python. That's not really a programming problem, it's just how to do it. So the next thing is maybe a little bit more interesting for you guys, these things called pseudo-random numbers. Yeah. So sometimes when you're programming something, you need a random number. You just need something random, and you're going to do something with it. But computers can't actually find random numbers. They follow, step-by-step processes. So they can't really do anything truly random. So instead, what we have to do with just a classical computer, a typical computer, is something called a pseudo-random number generator. And these are functions that generate numbers that appear random. Even though they're not actually random, they're random enough in appearance to suit our purpose. So what are some examples? Maybe you need to simulate a dice roll, like maybe you're programming a computer version of a board game or something like that. So you need to simulate a dice roll, or maybe you're teaching a statistics class and you want to teach about probability of dice rolls, but you don't want to roll a single die 1,000 times, so you would simulate it. Okay, so this is one kind of game thing. And there are many other games where you might need a random number that don't explicitly involve something like dice. You could think of any number of casino games where you have cards or a slot machine, and even modern video games. You might think of many times where something random needs to happen. Like if you're playing an RPG and you open a treasure chest, there might be some probability that you get a particular item. And what the computer would need to do is calculate a pseudo-random number to determine what you would get out of that treasure chest. Let's see, and random numbers also play an important role when you're doing simulations of physical processes. Like maybe you're doing something with physics or chemistry or aerodynamics. And there's some sort of probability involved. So that's sort of the idea, and some places where you might actually need them. And in practice, the way that you would, or that a computer would generate a pseudo-random number is usually through something called a linear congruential method. And this is actually something that uses the modulus operator that we just learned about. So what a computer would do in order to generate a pseudo-random number is that it would start a sequence like this, x1, x2, x3, using a formula. So the nth item in the list, xn, is equal to this, a times the previous number in the sequence, xn minus 1. Then you'll add a constant, c, and then take the modulus of that with respect to some number n.
Professor, the word between linear and method, what is that?
Congruential. Like the word congruent with IAL on the end. It's not really so important that you remember the word. But that's what this is called. So what you would do in practice is pick numbers, integers, to go in for these. So let's just make a choice and see how it would work. Let's try m equals 11. So this is the modulus. A, we're going to try 7. That's the constant multiple here. And then the number that we add, c, is going to be 5. And we also need a starting point. We're going to say x1 is equal to 3. And the starting point is usually what's called a seed. Okay. So x1 is, of course, equal to 3, the first thing in our sequence. And then x2, we would compute using the formula. So in this case, we had to have 3 times x1. So 3 times 3 plus 5. And then we compute modulo 11. What would this come out to? What would you get? Oh, yes, I did make a mistake here. Yeah, A is 7. Thanks for pointing that out. So 21 plus 5 is 26. Modulo 11. What do we get? 4. Good. Yeah, 11 times 2, and then the leftover is 4. And then to get the next one in the sequence, we would take this output and plug it back in. So you would do 7 times 4 this time, plus 5, mod 11. What would this come out to? Anyone?
0.
0, good. Yeah, you'll get 33 from this, and then modulo 11, 33 is 0. Good. And then this would just continue. You take your output and you plug it back in, and then you just keep on going. So the idea here is that you shouldn't be able to predict the next number in the sequence, at least if you don't know the actual process that we're using. Of course, if you know everything about the algorithm, you could tell exactly what the next number would be. But if you didn't know what the algorithm was, then these numbers should appear random. And what I want to do now is go back to my notebook and take a look at this sequence. And I think I need to change this C to be 5. Okay, so what I've written here is just a little snippet of code that will compute the sequence that we were doing by hand. The first thing in my sequence, my list, is 3, and then I have the 3 constant values, 11, 7, and 5 from the problem. And then this little for loop here is going to compute the next thing in the sequence and add it to my list. So let me just hit enter. So we can see the first 3 values, 3, 4, and 0, match up with what we computed by hand. And then you can see the next 27 or so values in the sequence. So does anyone see anything interesting, any patterns?
Well, after this number 6, it sort of loops back.
Yeah, so let me highlight this section, 3, 4, 0, 5, 7, 10, 9, 2, 8, 6, and then compare that to the next sequence of numbers. We have 3, 4, 0, 5, 7, 10, 9, 2, 8, 6. It repeats itself. Good. I think we have, what, 3 repetitions here of the sequence? So if this was actually a good pseudo-random generator, then there shouldn't be any patterns like that that are obvious to the naked eye. Because if you just start looking, you'll notice this pattern, and then your random number sequence that is just not random. And if you knew the sequence, maybe you could use it to predict like the outcome of a slot machine or a poker game or something, depending on the situation. And that has actually happened before at a casino. Someone was able to tell that there was a little bit of a bug in the code in the slot machine, and they took advantage of it to win some jackpots. So in practice, this wouldn't be very good. We would want actually much larger numbers that I have written down somewhere. Can't find them in my notes. So in practice, we would use much bigger numbers. So this is 2 to the 32 power minus 1. A is 7 to the 5th power, and I'm going to actually change C to 0. And if I make this choice, then we'll get a much better sequence of random numbers, as you can see. So you could try as hard as you wanted to, and you really just wouldn't find any pattern in this particular output now. And actually, this pattern doesn't repeat itself if you go out to something like 2 million numbers in the sequence. It would never repeat itself. So it looks like this is our stopping point for today. So does anyone have any questions before I close this down?
So, Professor, will you be able to help me with the homework tomorrow? Because I'm still a little lost about what to do for some of them.
Let's see. So tomorrow, my office hours are 10 to 12. If you want to set up a meeting,
Yeah,
does some time in there work for you? 10 to
yeah, should.
Okay. Yeah, so just send me a good time that works for you and we can try to work on a problem or two.
Thank you.
Any other questions?
Professor Odell, quick question, sir.
Yeah, go for it.
When's our next exam by chance?